Good morning, everyone. I'm Chris Rosbach, and I'm here to tell you today about Dandelion, which is a system I've been building with my colleagues Yuan Yu, John Curry, JP Martin, and Dennis Federley at MSR in Silicon Valley. So yeah, I sure wish that would go away from the bottom, but oh well. So this talk is primarily about improving the programmability of systems that feature architectural diversity and distributed compute. So why should you care about this problem? Well, data volumes continue to increase, and the cost of acquiring and owning a cluster continues to decrease. And there's a concomitant trend where architectural diversity in the form of accelerators like GPUs and FPGAs represent an increasingly attractive avenue for improving performance in a lot of application domains. So something like a small cluster of GPUs and CPUs is going to be an increasingly common kind of compute substrate in the future. Unfortunately, a system like this remains very, very difficult to challenge. To program and to challenge. The challenges include the presence of heterogeneity, which forces the programmer to deal with multiple APIs and programming models, each of which typically requires significant specialized expertise. And of course, distribution and concurrency bring with them a long list of problems that are very well explored in this community, arising around data movement, scheduling, synchronization, and consistency. So the goal of Dandelion is to make this kind of system much, much easier to program. So the grand vision of Dandelion, or its holy grail goal, if you will, is to provide a single uniform programming interface across clusters comprising CPUs, GPUs, FPGAs, and why stop there? You name it, right? And in this grand vision, the programmer writes sequential code, preferably in some productivity language like Java or C#, and the runtime is responsible for absolutely everything else, parallelizing the computation, mapping it to diverse architectures, partitioning, scheduling, and so on. Now, while this holy grail version of the problem statement is a very good way of understanding what we're trying to do, what we're actually doing in the system that I'm going to tell you about today is somewhat more modest. The current Dandelion prototype offloads data parallel code fragments to a small cluster of GPUs and CPUs. And the starting point for our line of inquiry was to focus on LINQ, and I'll have a little bit more to say about that shortly. Now, while relative to the last slide, this might seem like a very modest goal, it's actually still quite ambitious. There are a lot of challenges that arise, particularly around mapping the compute to diverse architectures, marshalling and moving data, scheduling. And in today's talk, I'm going to give you a sense of how we address some of these challenges. So here is an architectural, high-level overview of Dandelion. Across the top of the screen, you see a client that runs a user program, and across the bottom is a cluster of some number of machines. And when the user program runs on the client, it is accepted by the Dandelion compiler, which produces 3 Dataflow graphs, each of which represents the computation at a different layer of abstraction in the technology stack. So there's a cluster scale Dataflow graph, which represents the entire computation, and each vertex in that graph will have a machine Dataflow graph and a GPU Dataflow graph. Now in these graphs, vertices represent computation, edges represent communication, so the compiler must also produce the code at each of these vertices. And this can be code that runs on a CPU and or a GPU. Now, at the cluster, there are 3 runtime components, the cluster runtime, the machine runtime, and the GPU runtime, which collaborate to schedule these Dataflow graphs onto the available resources. Now, this is a bit of a static view of the system, so I want to take another look at it from a slightly more dynamic view. So again, we have a user program and a cluster with some servers that have CPUs and GPUs. The Dandelion compiler takes the user program and produces the cluster Dataflow graph that I talked about in the last slide. The cluster runtime is responsible for dynamically mapping vertices from that graph onto the machines in the cluster. It's also responsible for supporting the infrastructure that enables these vertices to communicate, implementing the edges in that graph. Now, if we drill down further into each of these vertices, what we'll see is a machine graph, also produced by the Dandelion compiler, and that may in turn comprise any number of GPU graphs, also produced by the Dandelion compiler. And particularly for the GPU graph, the compiler targets a primitive library of generic relational algebra primitives. So this is a very large, complex system. I'm not going to have time to give you the details about all of it today. So instead, I'm going to focus primarily on the problem of mapping the user program to the different architectures that are available at each machine. And for the remainder of this talk, please bear in mind that if I say user program, what I really mean is LINQ query. Now, if you happen to be in the subset of the audience that responds to hearing that by saying, wait a minute, what's a LINQ query? You're in luck, I'm going to tell you. A LINQ query is a language integrated query To first order, you can just think of it as first-class language support for relational operators over collections of objects. And I have an example here that sort of gives you a feel for what it looks like. I have some collection, and I'm using familiar relational operators like where, and GroupBy, and select. And these operators accept user-defined lambda functions or anonymous functions. So why do we choose to focus on LINQ? Well, there are a number of good reasons. First, it expresses a lot of important workloads very easily and succinctly, things like k-means, PageRank, and more generally, MapReduce. Second, the fact that it supports these lambda functions makes it very, very powerful. It effectively embeds a very large subset of C# or whatever the front-end language is within that framework. And finally, it's declarative and data parallel, which makes it a very natural fit for Dataflow and for lazy evaluation, which is a property that is going to feature prominently later in the talk. So for the next several slides, I'm going to try to give you a sense for how Dandelion works by focusing on a particular workload, k-means. It's a machine learning workload, and it partitions some number of points into k clusters. You don't really need to understand it in depth, but some intuition helps. The algorithm works by initially picking k centers, and then iterating, first mapping each point in the input to the nearest center, and second, recomputing the centers as the average of all the points that map to those centers. And as you perform these steps iteratively, eventually you converge to the clustering you want. Now, I like using this as an example for talking about Dandelion because it can be implemented almost completely by this single LINQ query. It's a GroupBy followed by a select. And the GroupBy is essentially implementing step one, mapping each point to a group that represents the nearest center. And the second step is performed by the select, which computes the average of all the points in each group. Now, parts of this have a fairly intuitive, I would assert, mapping to a GPU, something like a select. Very easy to see how this can be parallelized. Something like a GroupBy, I put it to you, is not entirely as obvious. And to understand why this is the case, you're going to need some background, not least of which is an understanding what GroupBy actually does. So for those who are not familiar or a little rusty, GroupBy groups a collection by key, and it uses a user-defined lambda function to map elements to a key value. So to illustrate this with an example, suppose you have some list of integers, and you perform a GroupBy with a lambda that maps each element to itself. The result is a set of groups which have uniform integer values. And naively, you might implement this simply by iterating over all the points in the input, running this lambda function, finding the group associated with the key, and then appending the element to that group. And I would even assert that parallelizing this using traditional parallel abstractions is relatively straightforward. You need some additional mechanism to partition the input, which I've somewhat blithely represented with a yellow PF partition function. And you need some additional mechanism to synchronize group creation and group addition. Now, you might have some sense that I'm going to tell you this doesn't work on a GPU. So understanding it, though, requires, again, a little bit of background. So with apologies for those who are super familiar with GPUs, for those who are not, you can think of it essentially as a very wide SIMD or vector machine, consisting of some number of SMs or streaming multiprocessors, each of which in turn comprises some number of processing elements. So for example, the GPUs in our Dandelion cluster each have 13 SMs, each of which in turn has 192 cores. Now, the programmer writes code for these machines as kernels, somewhat confusing in this community. And these kernels are expected to be able to make use of thousands of lightweight hardware threads, which are further explicitly subdivided by the programmer into blocks to enable some important inter-thread communication patterns. Now, in the programming model, all of these threads execute in parallel, but really what's going on under the hood at runtime, the hardware is mapping subsets of these blocks, called warps, to the SMs, and switching frequently between them to tolerate things like memory latency and divergence of control flow. Now, it's traditional in any GPU-based talk to devote some time to bemoaning the proliferation of programmer-facing microarchitecture. But I'm going to skip that, and instead, rather than drag you through all of these bullet points, I just want to call out the things that you really need to keep in mind to understand this talk. Any performance-profitable GPU offload requires that your algorithm be able to use thousands of threads that run in parallel, and due to idiosyncrasies that arise around how the hardware maps these threads dynamically to the compute substrate, traditional synchronization mechanisms like locks are untenable if you have shared mutable state. So if you think back to the strawman implementation of a GroupBy that I showed you in the previous slide, this is out of the question due to both of the limitations I just told you about. So how do we actually perform a GroupBy on a GPU? Our approach is to process each element of the input in parallel. And we take advantage of the fact that grouping is fundamentally very similar to shuffling. So if there's a thread looking at an input, its job is to write that input at an output that corresponds to a contiguous layout of all the groups. But to do this, the thread needs to know the start index of its group, which requires knowing the start index of each group, which in turn requires knowing the number of elements in each group, which further in turn requires knowing the number of groups and the input to group mapping. So there's a very, very real chicken and egg problem associated with taking this approach. And we solve this by performing the GroupBy in multiple stages. So again, mapping a single hardware thread to each element of the input. In the first stage, we're only going to try to figure out how many unique groups are represented in the input, and we'll assign some synthetic group identifiers to each of these groups. In the second stage, we'll again look at the data and the output of stage 1 to try to compute the group sizes. We can then perform a prefix sum over the group sizes to find the offsets of the beginning of each group in the final output, and in stage 4, we perform a shuffle. Now, we can implement this on a GPU without using things like locks, because it is possible to perform stage 1 with a GPU-based lock-free hash table. It's possible to perform stage 2 by doing a lookup into that hash table and using only per group atomic counters. Stage 3, a prefix sum, is very, very well studied parallelization technique in GPUs. And then finally, the final shuffle, again, can use only per group atomic counters. Now, why have I taken the time to go to this level of detail about how to implement a GPU-based GroupBy? There are a few reasons. The first is to make the observation that the user types and functions that are in the original query are not actually referenced at every step in this problem decomposition. In fact, they're only referenced at the places where I've redrawn the text in red. Second, and more importantly, the data flow here is actually abstract in the sense that if I've solved a GroupBy for integers, I've solved it for essentially arbitrary types, which strongly suggests that an approach based on data flow and generic primitives is going to be a good one. And in fact, this is precisely how Dandelion works. The Dandelion compiler targets, as I said earlier, a library of generic primitives, and it includes things like building a hash table, which is parameterized with types for key type, element type, key extractor function, and so on. And supporting a generic GroupBy primitive simply boils down to composing these primitives, as I've drawn in the data flow graph on the screen. Now, building a compiler that runs LINQ on GPUs is essentially a matter of iterating this process until you have support for all of the LINQ operators. One nice thing is that we found that many of these primitives are reusable in building other operators. For instance, hash tables and prefix sums wind up showing up very commonly. Now, there is one piece of the puzzle, though, that I haven't quite told you about yet. Recall that in the original query, the types, the key type and the element type, this is C# code, right? And to instantiate this data flow graph on a GPU, I need these types in GPU land. So there's a cross-compilation and marshalling step that needs to be completed as well. So to illustrate how we approach this, I'm going to return your attention to our k-means code, and we're going to look at the nearest center method that is used in the lambda for the GroupBy. I'm showing you the code here, but I don't really expect you to read it. I just want to use it to illustrate 2 points. The first is that if we're going to cross-compile this method, we also need to cross-compile all the methods that it calls. Second, and somewhat more sticky, is the issue of dealing with the types themselves. This vector type is a C# type. It's a pointer-based structure. It has things like vtables. You can't simply pick it up and move it to the GPU and hope that it's going to be usable. So we need to decide dynamically on a GPU-side layout for objects, and additionally generate some code that will dynamically serialize objects and deserialize them between these 2 representations. And we do this by performing a translation at the .NET bytecode level. And this translation maps C# types to CUDA structs, and it translates C# methods into CUDA kernel functions. Additionally, we generate the C# code that performs the serialization and deserialization to translate between formats. Now, this doesn't actually work in absolutely every case. There are definitely constraints, but the primary one arises around dynamic memory allocation, which is not exactly unsupported, but certainly poorly supported on GPUs. And so when we encounter dynamic memory allocation in the code we're cross-compiling, We will convert it to stack-based allocation if we can detect statically the object size. And otherwise, we're going to fail the GPU for parallelization and roll back and use a CPU-based parallelization approach. So we're still able to get a correct answer, even if we can't parallelize for the GPU. So giving you a sense of what this looks like in real life, here in the right lower corner is the actual nearest center code, and here is the dynamically generated CUDA kernel code. Again, I do not expect you to read it. I just want to illustrate that the vector type winds up being translated to a kernel struct _0 type, and our nested calls wind up translated to other calls into CUDA kernels. So to start putting all these pieces together, I told you I was going to talk a little bit about lazy evaluation. Dandelion works by leveraging the lazy evaluation property of LINQ. And this means that it doesn't actually do any work until you try to use the LINQ query. So if we step through our k-means code, here's the actual query. At the point in the program after that line executes, nothing has really been done yet. All that has been returned from the query is an expression tree. And it is not until later, when the user code attempts to enumerate the result and look at objects in it, that Dandelion gets invoked. And at this point, it will load the binary for the currently running executable, find the IL for the types and functions used in the query, generate C# serialization code and CUDA kernel code, invoke the C# compiler and the CUDA compiler, build the 3 Dataflow graphs I started the talk telling you about, deploy to the cluster, and run. So again, giving you a feel for what the final thing looks like. Here's our actual cluster scale k-means Dataflow graph, and it features across the top 10 GroupBy nodes. That's one for each of the 10 machines in our Dandelion cluster. And if we drill down into each of these nodes, what you'll see is a machine graph and a GPU graph. And I've circled in red the subset of the GPU graph that represents the GroupBy graph that I told you how we build. So hopefully at this point I've given you some sense of how Dandelion works, and I want to move on and give you a taste of the evaluation that's in the paper. So we're really interested in 2 questions in our evaluation. First, have we improved the programmability of the system? And second, if so, at what cost in performance? What is the trade-off between performance and programmability? And we examine this in both the single machine context and the cluster context, using a number of benchmarks, k-means, PageRank, TerraSort, SkyServer. I encourage you to look at the paper for details. I also encourage you to look at the paper for details of the platform, which is our 10-machine cluster featuring NVIDIA Tesla K20Ms and 2 Xeon chips for a total of 24 hardware thread contexts. So let's begin with the programmability question. Here is the complete code for k-means in C#. I'm showing it to you again, not because I expect you to read it, but because I want you to compare it to the complete implementation in Dandelion. Want to see it again? OK. Here it is in C#. Here it is in Dandelion. So in truth, this slide is actually even more effective if you don't have to admit that there is some programmer effort. But there is some. So we do need some hints from the programmer to tell us when we are dealing with a case where GPU offload might be profitable. And there are a number of subtle caveats around this that I'm not going to discuss today. I encourage you to please look at the paper if you find this interesting. So hopefully you're willing to concede that maybe we've improved programmability, but at what cost? So to make sure that we had completely, or at least with some fidelity, characterized the trade-off space between programmability and performance, we wrote 15 different versions of k-means based on different tool chains and different parallel programming approaches. So in this graph I'm showing you, along the left are a number of C#-based implementations, both parallel and sequential. All through the center are a number of CUDA implementations, each of which exercises increasingly sophisticated microarchitectural features and investment of programmer effort. And on the far right is the Dandelion implementation. The green bars are the speed up over a sequential C++ implementation of k-means. And the blue line is the number of lines of code in each. So what you really want is a very low blue line and a tall green bar. So the trends I'd like you to take away from this are that for the C# implementations, they do have low complexity, but they tend to be slow. And in fact, even our multi-threaded C# implementation is only 7 times faster than C++ sequential on 24 cores. By contrast, the CUDA implementations are very fast. However, they also have a lot of complexity. And I want to emphasize that the number of lines of code doesn't really tell the whole story here, right? Significant expertise is required to eke out these last bits of performance from a GPU. And then finally, Dandelion has both low complexity and good performance. It's 20 times fewer lines of code than the most basic CUDA implementation. It's 17 times faster than sequential C++. And it's in the range of 2 to 7 times slower than our best hand-optimized CUDA implementation. And this range arises because we evaluate with different data sets. So, I've talked ad nauseum about k-means. You might be wondering by now, does this generalize? And I put it to you that it does. So I'm showing you in this graph the performance of all of our benchmarks on a single machine. Again, it's a speed-up graph. And the baseline here is a sequential link implementation. That's the little pink bars. And we're comparing the performance or the speed-up of a multi-threaded CPU-only Dandelion with 24 threads and a GPU-only Dandelion. And the trends that you should observe here are that in many cases, particularly those that feature naturally a high compute-to-data ratio, we can get very good speed-ups in the range of 15 to 20x, and we're generally about twice as fast as a 24-core implementation. And of course, over to the right, there are cases where the situation is not so rosy. Dandelion is still able to come up with an implementation that is faster than sequential, but it's not significantly faster than leveraging multi-core parallelism. Now, I began the talk by asserting that this is a good tool for dealing with distributed environments, so I'd like to end the evaluation section by showing you the performance of Dandelion on our cluster. The baseline has changed in this slide. Again, it's a speed-up graph. The baseline is Dandelion using only one thread of one core at each machine in the cluster. The darker blue bars are 24 cores per node in the cluster. And then the lighter blue bar is Dandelion using only a GPU. Things to observe here are that, as you might expect, moving into a distributed context, overheads are introduced that eat away a little bit at the performance gap between the GPU and the CPU. So for TerraSort, we're still faster with a GPU than we are with multi-core CPUs, but not as much as we are in a single machine context. For SkyServer, the win that we see in the single machine context completely erodes as we move to scale because the data sizes are much larger and the GPU memory is tiny. So it's actually 2 orders of magnitude smaller than the CPU memory on these machines. And what happens is that the underlying GPU runtime, which is ptask, winds up thrashing, moving data in and out of GPU memory on demand to satisfy allocation requests from upper layers. And then finally, k-means, which is a bit of our, obviously you might have detected it's our poster child application by now. It's 66 times faster than the system using only one thread per node, and 4 times faster than 24 cores per node. And this is achievable not just because the application is fundamentally compute-bound, but also because as you move into a regime where the data is much larger than GPU memory, it's still possible to stream the data set through memory without incurring a synchrony penalty. So with that, I would like to touch briefly on related work. There's a lot of text on this slide reflecting the fact that there's a lot of related work in a system like this. There's actually over 100 sites in this paper, and I already know of a few that I kind of wish we had cited in retrospect. But I do want to call your attention to one item, which is at the top, a paper called Linkits, which is a paper in this year's ISCA that used the Dandelion compiler as a front end for an FPGA back end. So hopefully that lends some measure of plausibility to the holy grail problem statement that I started the talk with. So to conclude, I'd like to reiterate, Dandelion is an end-to-end system that provides high-level programming abstractions for heterogeneous distributed systems. And I think we've made a good case that it is possible to improve the programmability of these systems significantly. However, while the current results are very promising, I also want you to remember they are incomplete. There's a lot left to do, particularly around query planning, better scheduling, looking at more applications, and generalizing to more execution contexts, more hardware diversity, and of course moving beyond LINQ. So with that, I'd like to thank you for listening to my talk, and I'll take any questions.
Hi, Ken Berman, Cornell. I really like this work. I think it's awesome. You told us a little bit about how Dandelion is really compiling at the GPU level in terms of these basic building blocks, but you didn't tell us anything about the distributed equivalent. So can you give us some idea of what the distributed building blocks that you're working with are as you map your problem to these higher level?
So what do nodes in the cluster scale graph look like? Is that
yeah,
what you mean?
and what is Dandelion's tactic for parallelizing across nodes as opposed to within the GPU?
Oh, okay. So to first order, you can think of its tactic as being fundamentally similar to the approach Dryad LINQ takes. Right? It's partitioning and replicated compute at stages. Right? And then we take advantage of the fact that we've already got a data flow graph there to compose lower level data flow graphs that leverage the GPU. There are some interesting tidbits that having a GPU as the compute substrate underneath these higher level stages introduce, particularly the need to avoid the file system, to actually be able to manifest a speed up from the GPU. But I think that for somebody trying to understand how it's built, you can just take that comparison.
Hello, Malte Schwarzkopf from the University of Cambridge. So I like this work a lot, but one thing that seemed quite curious to me, and that is that you do the translation at the .NET bytecode level. Mm-hmm. So it would have intuitively seemed to me that doing it at a higher level, so from an abstract syntax tree in a sort of, or even a source-to-source transform would be better because you have more semantic information and therefore your job might be easier. Can you comment on why you made that choice?
Sure. So the short answer is that we can get the AST from the IL. So it is effectively a source-to-source translation. That said, there are other advantages to doing it at the bytecode level, which are that that's a shared format that is targeted by multiple front-end languages. So by doing the translation there, we get for free, modulo some caveats, support for any other .NET language. So the limitation that you suggest is there is not actually there, and by doing it at .NET bytecode level, we get more language support and more generality.
Okay, thank you. That makes perfect sense.
Let's take a question from the moderator page. This is a very popular question. What would be the additional difficulties? What would be the additional difficulties in building a system similar to Dandelion to support something broader than LINQ, e.g., a subset of C? Would a similar approach still be viable?
Well, there are a lot of challenges that arise there, right? I mean, of course you could do it. How's that? No, thank you. Thank you. Next question. No, I mean, the fact that we're working with this, it gets back to the last question, which is that by working with the .NET bytecode, we actually have very, very rich type information to do a just-in-time cross-compile that would be much, much more challenging if C is the front end. So that's the first order.
Last question.
Karthik Nilekant at Cambridge. So just looking at those hand-optimized k-means implementations, a lot of them seem to take advantage of memory coalescing to sort of get the gains over your system. Can you talk about what's sort of the fundamental challenge of building that into what Dandelion does, whether you're planning to incorporate some of those things in the future?
Yeah. So memory coalescing, for those who are not familiar, basically, ideally, when you write a GPU program, you want to set up your data and map your threads to that data such that multiple threads can share memory loads. And this is actually winds up being kind of a first-order determinant for performance in a lot of cases, which is why, as you observe, the memory coalescing features prominently in these CUDA implementations. So we have thought a lot about how to do this automatically, and we have built some infrastructure to instrument the low-level runtime and figure out what is the actual memory efficiency of our implementation. And then the next step is, of course, taking that information and deciding when we get an observed low memory efficiency reading, how do we rearrange things so that we can actually coalesce memory. Some things are obvious, right? If you change array of structs to struct of arrays, then for workloads where the data structures can obviously be rearranged that way, you're going to win. We were careful not to say that we could do it automatically because I don't think that's a property of every workload, right? So does that help? Okay.
Okay, let's thank the speaker.